1, function, sections 1, 3, and 1, 4. So what are functions? Well, before we can talk about a function, we have to define something called a relation. So usually what I do when I start talking about this is I want you to think of a relation as think of every person on the planet. Okay? That's kind of like would represent a relation. And then what we're going to do is we're going to look at those things that are called relations, but we're going to look at specific types, which are called functions, which would be like just the population of the United States. So you have a bunch of people are relations, and then we're going to look at things called a function. So what is a function? That's our main purpose here. But before I do that, what's the relation? A relation is simply a rule that establishes some kind of relationship between two quantities. One of the quantities we're going to call an input for right now, and the other one we'll call an output. That's what a relation is, some kind of relationship. It can be all kinds of different things. So then what is a function? What is the specific type of relation we're going to focus our attention on? Okay, a function. Here's a simple definition. Is a relation where for each input there is exactly one output. That is the definition of a function that you're going to need to remember. For every input, there is exactly one output. So in an equation setting, it'd be like this. If I take in an equation and I plug in the number 3, I'm going to get an answer. I'm not going to get two answers. I'm going to get a single answer when I plug in 3. That's what it means. For every input, there is exactly one output. Okay? We can describe functions in 4 ways in here. We're going to look at it in words. We're going to describe things in words or a table, equation, and a graph. So when we do that, we want to make sure we can recognize that we actually have a function, because when we have a function, certain things are going to work or apply. Anyway, so let's move on to the new word types that we're going to see. So we talked about for each input, there's exactly one output. Well, the input values, the things we call inputs, actually have a real name that we're going to be using from this point forward. We can interchange it still, but input values are domains. That means we're talking about our domain. So when I talk about a domain, these are the numbers that I get to put into to plug in, the input values. The answers I get, those are the output values. Those have a name called the range. So when we talk about this in the future, the domain is the input values and the range is the output values. So that's the definitions that we use later on. Why is this important? Why do I need to know the domain and range? Because you're starting to do math where the domain and range plays a major role. Okay? And really, how does this manifest in the real world? As you can see what I have written here. So the domain describes what kind of input values are allowed. And the range describes what kind of output values are going to look like. And why is that important in the real world? In the real world, we're going to gather data. You try and find a pattern, is what we've been doing, patterns, correct? And try and come up with some kind of rule that describes that pattern. Well, when you find a rule and you separate it out, so for example, we might have had an equation that looks like, just a simple, let's do a simple line equation. Let's do x plus 1. Then we had a rule that does this. Okay? Whatever this is. Okay? But in the real world, this could represent something like the number of people going up the stairs. Okay, so if X represents the number of people, right, or the time, or whatever we talk about, let's say X represents time, and Y represents the number of people. I don't know, that doesn't make any sense, but you get the idea. Well, let me ask you a question. If I look at this, this has an inputs, I can plug in everything I want. I can plug in positive numbers, I can plug in negative numbers, I can plug in 0, I can plug in all kinds of stuff here. I can plug in fractions. This is an equation, it's a formula, right? But in the real world, and you plug in negative time, what does that even mean? Negative time, wouldn't that be like time travel? Right? What's a negative 3 hours? Okay, well, that's in the past, isn't it? And you're not there then. So what about, I can get negative answers. If this represents the number of people in the real world, can I have negative people? What does that mean? See, this is why we need to understand domain and range. It restricts what we can actually do in the real world. It makes the answers make more sense. Most of you doing math in the real world is all done on computers and stuff like that. You're not going to really do much hand-drawn mathematics that you do here in class. Okay? So what do you need to know? Well, you need to know what numbers to plug into the computer. Because it's just a machine. It doesn't know what's right or wrong. You as the operator have to know what's right or wrong. So the domain and the range play a very important role. You need to set things up so that you know what numbers go in, and you need to make sure that the answers you get from the computer are actually make sense. So you have to understand what kind of answers I'm supposed to get. So that's the range. This is why this is important in the real world. Okay? So we're going to be looking at domains and ranges. We'll talk about those a little bit. We have function stuff. So let's go ahead and look at some of the things that's going to pop up when we talk about functions. Once I have something as deemed a function, all right, and I haven't showed you how to figure out it's a function yet, but once I know something is a function, it gets a special name, okay? Function notation is what we're going to talk about right now. A lot of times they just throw this at you guys and they don't really explain it all to you. So normally if I write an equation like I did before, we use y equals, and then we have a bunch of some other variable, x, most likely. When I have function notation, and that means it's a function, that means I know for a fact, and I have confirmed that for every input, there is exactly one output. That means once I know that is true, then I get a special function name. So the y, just so you know, this is going to be a function, okay? The y value, the output value, takes on a new name. So this is called the equation for y. Because it's a function, I can now change this y into a function notation. And we call it something like that. If this would be f of x equals x plus 1. So what is this thing? And we need to learn to recognize for what it truly is. It has two parts. It has the name, f, and then it tells you the variable of the expression that's going to come next. This is the function whose name is f with the variable x. That's what it means. We usually abbreviate that to just simply say f of x. F is the name of the function. This is the name. It's the name, and this is the variable that is going to be used. Okay? It has to be two parts. This does not mean times. When I see something like this, it means function notation. Okay? It's very, very important that you kind of remember that. Okay? Do I have to use the letter F all the time? No. You can use any letter you want for a name. Do I have to use the letter X all the time? No. I can use any letter I want to represent the variable that's in my equation. I can do h of t. This is the function whose name is h, and the variable will be t. It's no big deal. They're just things that kind of represent stuff. But know that I can use many different things. They don't always have to be f and x and stuff like that. Now, normally what we do is we start with the function f. The most common ones used are f, then g, then h. But you can use any letter to represent a function. Any letter, okay? And you can use any letter to represent a variable. Just don't use the same one twice. Don't use the function name f and a variable name f. Don't do that, okay? That gets kind of weird. But that's what this is. So this is what function notation means, okay? And we'll explore this a little bit more and as we go out throughout the day. So how do I represent and recognize whether or not I have a function? Remember, there was a bunch of different ways to look at stuff. So we're going to look at a function in a couple of different ways. And I'm going to show you how you can determine by looking at it whether it's a function or not. So with that, I'm going to go to this handout I gave you. And the first one right here, this is called a mapping diagram. And we want to decide if any of these represent functions or not. So remember, the definition of a function is for each input, there is exactly one output. So let's look. If I look at this one right here, and we're just going to put in yes or no. And if it's a no, we'll try and describe why it's not. If I look at this one right here, here's the input. Does each input have exactly one output? And the arrow shows you the output that it's going to go to. So if I have a 1, I'm going to get a 5. A 2 gives me 6. 3 gives me 8. And 4 gives me 7. The definition is, does each input have exactly one output? Yes, this is a function. Now, this is called a mapping diagram, but it's also very similar to a table. Okay, so we'll get to those at the bottom down here. Let's look at number B. Does this satisfy the definition? Look at the input. Does each input have exactly one output? Yes, it just all happen to be the same output. But if I give the number 1, is there an answer for number 1? Yes, it's 0. Does 1 have another answer besides 0? No. How about 2? Does it have an answer? Yes, the answer is 0. It's okay for it to be the same, but each of these can only have 1 going off of it. You see that? So if you think of it that way, this one is yes, it is. Would this one be? So now you can see clearly why this one fails. Okay, look at the input. They each have an output, but what's the problem? Is the number 9. 9 has 2 outputs. 2 arrows coming off of 9 means that this input does not have exactly one output. It has 2 different outputs, so this is not a function because of that right there. So what about graphs? What if I look at a graph? Can I look at a graph and tell me if it's a function or not? Well, yes, if you understand the rule that we use. And it is called the vertical line test for functions. Usually we just call it the vertical line test. If any vertical line drawn through a graph intersects or hits the graph more than one time, then the graph is not a function. That is the vertical line test. Anywhere I can draw the vertical line anywhere. Vertical lines go up and down. If I can draw any vertical line, not every, but any vertical line, and I hit that graph more than once, then that graph is not a function. If it's a function, it can only hit it once. Remember, because a vertical line is an x value. For every x, there is exactly one y. So this one right here would be a function. There is no vertical line I can draw that will hit this graph more than once. So this one is yes, a function. This one's a little bit harder to read. If you look closely at your copy of it, there's a dot here, 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 and here. They're just dots. Only the dots are the part of the graph. So if I draw a vertical line through any of these dots, do I get hit more than one dot? Only in that spot right there, correct? Because that line right there, I drew a vertical line through this graph, and I hit 2 dots at the same time, this then is not a function. It fails the vertical line test. What about this last one over here, F? Well, there's a vertical line right there, and you can see clearly that it hits the graph 2 times. So this one fails also. So this one is a no. So that's the vertical line test for graphs. For a table, because you only see a limited number of points of this graph, you don't know exactly what it is. You're not asked to find a rule. Based off of what I see, would this be a function or not? Well, this one is very similar to the mapping diagram. So if you think about it, look at the input. If you don't see a repeat in the input, then it's going to be a function because you don't know what anything else. So each one of these maps to a single number. You're good to go. This one would be a yes. Here, it looks like all these go to a different output, correct? But what do you notice? That input happened twice, didn't it? That means the output better be the same number also. And you just accidentally wrote it twice, but it doesn't. 2 goes to 2, and 2 goes to 4. So this would be an example like this one, where it goes to 2 different answers. So this one then fails as a no. What about this one over here? Well, look at the input. There are no repeats in the input, correct? Does it matter that this went to 1 and this went to 1? That does not matter at all. It doesn't matter about the output. Only one input. For each input, there is exactly one output. You can't have more than one output, but it can be the same output. It just can't be one input with 2 different outputs. So this one would be a yes. So that's how I can determine functions, by looking at things in a table, a graph, mapping diagram, very, very quickly. For the equation, I'll talk about that at another time. So on this side over here, this is about evaluate. When you see the word evaluate, they want you to find a number answer. Evaluate means to find a number answer. Solving doesn't necessarily mean find a number answer. Evaluate means find a number. Solve just means to solve for whatever that variable is supposed to represent. Sometimes it's a number, sometimes it's not. So how do I evaluate this? So whenever we did our table stuff, this is basically how we build tables from rules. Here I have a rule that's a function, h of x. It is 3 times something plus 6. X is a something. And they want you to tell me what, when x is -3, what I would get. So you're like building your in and out table. Here's your input. This is your output. Okay? And we want to plug in 3 and tell me what the output would be in our rule. It's kind of what we're doing here. Here is how I want you to write it. So if x is -3, you will go over here and you will replace the x with a -3. So that is h at -3. This means the value of the function h at -3. That's what this means. The value of the function h at -3, which simply means to plug in -3. When you plug in any number into any formula of any type at any moment in this class, you will always plug it in using parentheses. Every time. So your first step here will look just like this. I don't care that you can do it in your head. You will write 3 in parentheses, -3 plus 6. You need to write that down just like that. After this, you can just give me the number. If you need to do more work to simplify it all out for yourself, that's fine. But for some of you guys, if you can see this, you just need to give me the number now. 3 times -3 is -9. -9 plus 6 would be -3, I hope. Okay? And so then when x is -3, h of -3 is -3. That's how that works. What about 0? Same thing. H of 0 is 3 times 0 plus 6. And then you can work that out and get an answer. And plug it into your table. This is how it works. H of 2. 3 times 2 in parentheses plus 6. That's 6 plus 6 or 12. And there's that. So this is what I'm going to be looking for. I want to see you plug it in. Then you may give me the answer. And then you put it into your table. This is how it works. This is how you evaluate functions. We will continue this off the video, but that's how you are going to do all of these problems exactly the same way. So let's go look at this over here. You'll see that this is more of the same. Okay? In this case right here, so classwork 1.4, it's just repeating the same thing, and I evaluate things. This one over here is a comparison. Can I compare the values of this? This is something you must be able to do also. Okay? So what do? Evaluate, find me a number answer for f at 3. The value of the function f at 3. Well, f is right here. Do what I just showed you. And you would do this. You're not going to have enough room to do the work here. You'll have to do this on another piece of paper. But you would have 2 times 3 plus 5. And then you can work this out and get the answer. 6 and 5 is 11. So f of 3 is 11. That's what you would have. And then you can do the rest of these. Some of these functions you may not know, but I'll show you h so you can see how that works. H of 3, here's h. It's 2 raised to the x power, which means this will be 2 raised to the third power. And 2 to the third power is 8. And so there's that. In the comparison part, I'll do this A1 here. You need to find f of negative 2, g of negative 2, and tell me which one is bigger or are they equal. So that's how you do that. So I'll leave that for you. What about this right here? Evaluate. Well, now there's other stuff involved. What does it mean to have a number out in front? It literally means find f of negative 4 and then times it by 2. That's what it means. This one means find h at 5 and then add a 1 to it. This one is find f of negative 1, find g of negative 1, and then add those numbers together. Okay? So that's what those things mean. So we will continue this process, and I'll talk about this one off air. And then this one is a people one. This is kind of like how it works in the real world. So let f of t be the number of people in millions who own cell phones t years after 1990. Explain the meaning of the following statement. So what does this mean then in context to that story? Well, f of t is the number of people in millions. The t is the number of years after 1990. So in comparison then, f of 10 means that t is 10, right? And so t being 10 means I am 10 years after 1990. That's what it means. And then this whole thing by itself represents the number of people in millions who own cell phones. That means this number here must mean the number of people in millions who own a cell phone. So how do I interpret this in context? What does this mean? That there are 100.3 million people who own a cell phone 10 years after 1990. Or you can redo that as what? In the year 2000. 10 years after that would be the year 2000, right? So you can say it that way also. Or you can say it this way. That is what you would write for that. So what would this one say? Well, don't overthink it. That means 20 million people, correct? This means the number of years after 1990. So once I have this one, it's easy to write the rest of them because this just says what? There are 20 million people who own a cell phone 8 years after 1990. Well, what does this one say? There are 3 million people who own a cell phone 20 years after 1990. See how it's just the same words, right? Well, this is written weird. Does it matter? No. Doesn't matter that it's written backwards, that this is on this side and it's not on that side. It's the same thing. What does this mean? There are 10 million people who own a cell phone 10 years after 1990. So that's how that works, and you would just write those sentences out, and that's how that, and so forth. All right? So that's what functions are. That's how we find them, and that's how we evaluate them. And I'm going to stop the video here, and we'll do some more problems together.